Siamo già online? No, okay, but we are already online, yes.
Yes, it's 10 minutes.
Cool. I will just take my notes.
Sure. There. There you go.
Oops. Okay, can we start? Hi everyone. Thank you very much. Thank you for being here tonight at this third appointment with Waiting for Pine 22. So after the first night on Italy, the second one with France, now tonight we are focusing on Poland. So this night will be dedicated to Poland. But before starting, I would like to say a few words about Pint of Science, what it is actually. So Pint of Science is an international organization working on science communication. It started in 2014 in UK, and then it spread quite quickly all over the world. So now Pint of Science teams exist in many cities, in a lot of countries. Why Pint of Science? Why we do that? Because we love science, and we think that science is important, and we want to bring science to everyone, independently on the background. And the best way to do that is trying to attract people in a relaxed environment, in a relaxed space like this one, like where we are today. So in a pub, in a bar, and try to chill a little bit and enjoy a pint of beer. And in the meantime, we can also listen to a nice talk about science. Everything, every field is present in Pint of Science. We're not selecting the topics, let's say. What?
Smoker.
It's fine.
Well, if you're not a smoker,
So as I said, the Pint of Science started in 2014, and now it exists in many countries, as you can see from this map. And the main characteristic of Pint of Science is that every year we organize a festival, a science festival, a 3-day event that takes place exactly in the same days all over the world. So every team working in Pint of Science is organizing an event that will take place this year from May the 9th to the 11th. So remember these dates, because you will find a lot of news on our social media, and of course on our website. So you can follow us on basically all the main social. And Pint of Science Norway is not only Oslo. Pint of Science Norway works in 5 cities currently. So there are 5 chapters. Tromsø, Trondheim, Bergen, and Stavanger are also part of our big, let's say, family. The first 2 years we were forced to go online for our festival, because with a perfect timing we decided to start Pint of Science Norway in 2020, so exactly the beginning of the pandemic. So this will be the first festival in person for Pint of Science Norway. So we are really happy about this. So please follow up. We hope you will enjoy. And if you will not be in Oslo on those days, just follow us, because you can find events also in other cities. So you could find something close. As always, this is the moment of the acknowledgement, and the biggest one goes to all the volunteers of the team that makes everything possible, and in particular to those that are working also on these collateral events of waiting for Pint 22. So Thibaut, that is also our national boss, and today is helping with all the IT stuff. Agnieszka, that is our social media manager, not only locally, but she's managing everything for Pint of Science Norway, so at the national level. And she will also, among all the other things, she will also chair the night today. But also Praveen and Lourdes that are not here today, but they're working really hard and they're helping a lot. So Lourdes is in charge of the quiz, and Praveen is our IT guy. Yeah. And of course, tonight we couldn't be here without our guests, so our speakers. So I would really thank you very, very much, because
We have a mistake.
what?
Yeah, because it's not. Agata Krzesinska will not say about climate change.
You're right. I thought my fault. My fault. My fault. No, it's right. But we could not be here without you and without your work and the time you dedicated to the preparation of this presentation. So I'm really sorry for this. But now I'm almost ready to leave the floor to Agnieszka. But before starting with the quiz, I would just quickly, if you want to play with us, because we are going to have a quiz now, you can play with Mentimeter. We are playing with Mentimeter. You can download the app or playing on using your browser. So this is the code. But before going on with the quiz, just another quick communication from Thibaut.
Yeah, it's the app. Okay, hi everybody. Where is my Mac? So we are doing something different today. We have a small app that you can, if you're a bit shy or if you're online. So we have, it's Copernicus in Oslo .glide.page. So here you have the profile of every speaker. So Nikolai, and you just scroll down, you have everything on the link. But you can also actually watch it again online later, and you can ask a question. So if you're shy, you just write your question, and everybody can see the question here, and you can upvote. So if you think one is better, well, you know what to do. You just upvote, and it will automatically rank it. And afterward, after the event, or when you feel like it, you can give us your feedback. We need it. So you just need to click. He will just give you, send you to a Google. It's a Google document still. Okay, the image is wrong. It's from last time. Sorry. And you can also share a picture with us if you want. So enjoy. So it's Copernicus in Oslo.glide.page. And now quiz time.
Yay!
You have them.
Yeah, can you
Come back to the presentation.
You can go to Mentimeter, I think, but
Yes.
present. If you could
You want?
present.
Okay.
Right.
Yeah.
There. Yes.
Is
Yes.
it the answer or not?
So it says there's not opening like this.
Present. Yeah. Don't say no.
I can play.
Yeah, now it
I
should
can
be
do the
okay.
quiz.
Yeah. Do you know the answers?
No.
Huh?
Sound is good. That sound is
Huh? The additional motivation for the winner, we have a beer. I mean, unless you want something else. But okay, we will wait 1 minute more.
Where is the code? Ah, yeah.
Find one error.
Oh, I have seen it just now. It's random, so it's not our fault, but we are sorry. Okay, people present at the break with us. Everybody's ready here?
Yeah.
Okay, perfect. Online, I hope everybody is ready too. So before we start with our speakers, we would like to test your knowledge. Of course, the questions will be about the future talk. So whatever doubts you will have during the quiz, you can ask later our speakers. So let's start. Oh. Yeah, what is meteorite? A piece of gold, a fragment of a star, a rock from a space. Time's up. A rock from space. And that is a correct answer. And who will be the first?
Oh, I'm third.
You're the boss. Okay. Next. Question number 2. How old is the sun? More than 4 billion years, more than 10 billion years, or maybe more than 1,000 years? I don't know. And yes, it's more than 4 billion years.
It's also more than 1,000 years.
This is what I was thinking too. This is what I was actually thinking too.
More than a village.
Oh, Copernicus was the one I was thinking about it actually today. Wow, the boss. Okay. The question number 3. Are meteorites hot or cold when they fall in Earth? Not really. They could be warm or cold. Yes. They are balls of fire. No, they will be frozen. Huh. Time's up. And the question is, the answer is not really. I was surprised too. Okay, let's see how the charts changed. Okay. Question number 4. How hot is the sun? 1 million degrees, 100 degrees, 5 to 15 million degrees Celsius.
Depends, is it today or 4 billion years?
More than 1,000 years.
Wrong units.
Oh, really?
It should be in Kelvin. No,
Okay.
it's easier to think this way.
Okay, so our expert says we have a mistake. It should be in Kelvins. We are so sorry. Really? Is it not? Okay. Have you know the answers?
No.
Okay.
Why?
How do you identify a fallen meteorite? Different colors and shiny. Wow. Magnetic, heavy, and weird shape. Or just weird shape. And time's up. So we can identify them by magnetic, heavy, and weird shape. Okay, almost everybody answered correctly. Oh, come on.
Seriously?
Okay, nothing, not a big change. Okay, we're almost finishing. Could there be life on the sun? Yes, no, we don't really know. And time's up. Oh, yeah. Actually, everybody answered correctly. Okay, our expert says no. And will we have a new leader? Nope. Okay. Last to last. Where is common for meteorites to fall? Tropical forests, deserted areas, the ocean.
Is it not town?
Come on, US, for sure, US. Everything happens to US.
Yeah.
And time's up. Wow. Really? Oh, damn. So we have mistakes in our quiz. We are so sorry. The ocean. No? Okay, so we will have the explanation from our speaker later.
So the one who got this four, they get a beer.
Boss. Two bosses, actually.
I lost my 7th place.
Yeah, you did.
See, Agata,
I know.
No.
Okay. Oof. Okay, so my boss, one of my bosses is out. Oof. Okay, so the last question. Oh, no, you're not. It's the second, sorry. Okay, so the last question. Why would the sun die out? Let's see if you get correct answers. Lack of hydrogen, lack of helium, or lack of heat? Oh no, it's not as simple as it sounds. Oh, lack of hydrogen. What our expert says. Okay. So who is the winner? Yeah. So congrats, everybody. I mean, congrats to Sian. Yes, applause, please. I hope that this person is present here, not online. Perfect, perfect. So during the break, you can come in and we will have a chat. What exactly you want? Okay, perfect. Thank you so much. Okay, something changed. Now you have to do the magic because I don't know Mac. Yeah. Okay, so now more or less you know what we will talk about. Yes. So our first speaker will be actually the expert on meteorites, Dr. Agata Krzesinska, and I have a little ściąga. So she's planetary geologist, and she's doing research on meteorites, like we said, but also on Mars. Since 2018, she works at the Center for Earth Evolution and Dynamics at the University of Oslo. She's a member of the Meteoritical Society and the Polish Meteorite Society, and she won several awards, such as the Lunar and Planetary Institute Career Development Award in 2013, and Willy Blackwell Outstanding Student Talk Award in 2013 also. So without any other delays, I'll give the floor to you. Wait. Oh, okay. Maybe just. It does not. Yeah, that will be better. Okay. Can you hear me? Yes, you can. So thank you for organizing this event, and thank you everyone for coming, and thank you for inviting me. As said many times, I will talk about the meteorites, and specifically will try to tell a bit more about how in this country, in Norway, meteorites are present, can we find them, and what to do to find them, and why actually to find them. So.
Oh.
What?
And that's it. Thank you.
Yes, thank you.
Okay.
The last one. Because I had the same slide in the beginning and end, and it was probably not previewed.
Oh.
Okay, so a couple of terms for the beginning. There are words like meteor, meteorite, meteoroid, and actually I'm very glad that in the test there was no mistake between meteor and meteorite, because it's something which I'm very sensitive to. So these are not the same things, meteor and meteorite. If you look here, they are obviously related, but word meteor.
Come back.
Meteoroid relates to a rock or a body which is in the space, like before entering the atmosphere. When this body enters the atmosphere in the Earth, traveling with a speed of few kilometers per second up to 72 kilometers per second, so very fast hypersonic speed, it starts to burn outside due to the friction with the air and starts to glow. And this glowing trail on the sky, which we sometimes call like a falling star, is called meteor, right? So that's this phenomena of light in the atmosphere. While meteorite is the rock which is left over this passage and makes it to the ground. So if we talk about a rock, it's a meteorite, never meteor, right? And this talk will be mostly about meteorites, although these other terms will also sometimes appear because they are related. And as a second sort of introduction, to make it clear where is science and where is fiction, obviously all of us know these movies, and this topic is quite hot in the Hollywood movies about death from space, and that's sometimes what we recognize meteorites mostly from. But obviously everyone knows that it's highly exaggerated, yet in reality we all heard about the fact that dinosaurs died because of the asteroid collision and it was deadly. Some of us probably have heard about the explosion over Siberia in 1908, where the forest was just what's the word, broken, and the seismic wave of that was even heard, detected in London, despite the event was over Siberia, so quite a devastating event. I guess many of us have heard in the media recently, in 2003, about the fall of meteorite in Chelyabinsk, which caused the breaking of the glasses and injuries. And maybe some of us saw this crater in Arizona, which is in the desert, like an open hole. So all this shows that events of catastrophic meteorites impacts can happen, but looking into the statistics, we can say that this kind of collision, like what happened to dinosaurs, may happen like not more often than once per 100 million years. So like no chance for us. The Tunguska explosion or Barringer crater formation event is 1 per millennium. So probably we will survive from that as well. We all, in everyone's lifetime, probably event like Chelyabinsk happens somewhere in the world, which means that if we are in a good place, we might be lucky or unlucky to experience that. But reality of meteorites, I don't know why. The other way.
Okay.
The real phase of meteorites is that we have like 10 times each year of fall of meteorite somewhere in the world. And actually, every day the Earth is bombarded by 100 tons of this dust. Can you see this part here? This is also extraterrestrial stuff. So probably during this talk, this kind of particle fell somewhere on the roof on the building here, and entirely unnoticed. And like thinking if meteorite falls are quite catastrophic, I don't know, this story is quite funny because as you can see here, a lady who was 18 years old had purchased a car from her grandmother and paid probably quite a lot for her, $400 for that. And a couple of days after or the next day, the car was hit by a meteorite and totally devastated. But actually, I don't know if it can be considered as a fatality because this car got very popular and was sold to a wife of a renowned meteorite legend, and they were able to pay $40,000 for this car just because it was hit by meteorite. So it's not that fatal. But apart from that, meteorites usually land quite safely and smoothly. And actually, I don't know how many of you can know that, but there was a meteorite fall in Oslo in 2012. And the story was that in 12th of March, the owner of cabin in Ridderløkka just came to visit the hut, the cabin, and noticed there was a hole in a roof. She called the local specialists to figure out what is there, and they realized that actually in this hole there is a piece of something which is meteorite. And this is the owner, the lady keeping the 2 pieces of meteorites. And a couple of days later, on another area in Oslo, so like the first meteorite was found here, and in Ekeberg area, another woman found another piece of meteorite. When people realized, okay, there must have been something bigger, that we are picking the pieces from everywhere, and started to search like more regularly to be observable to that. And they started to find some like small pieces, a few tens of grams in mass pieces on the snow. Actually, the event became so popular that few days later, other people from abroad came, and this is a crew of Polish people who came to search for meteorites in Oslo, and as you can see, quite successful. So this meteorite became quite popular. And yes, please. And just for you to have an image of that, it's like Ridderløkka, a piece more or less of the size of apple. And in Ekeberg Sletta, another piece of apple size and a couple of plant size meteorites, right? So actually, it would be extremely easy to overlook it if it wasn't something special, or if you did not know that there was a fall around and you have to look for it. Okay, thank you. And thanks to the Oslo meteorite was moved to the collection in the museum, stored and exhibited there, and was very loud in the media, which caused that a year later, a person went for a fishing trip to the mountains, and out of sudden, in the open area above the tree line, they found out this piece. And because he knew from media how the meteorites look like after the Oslo fall, he again contacted specialists, and it turned out that it's a meteorite. So entirely lucky person with a totally different highlight of the day probably than he meant. And both meteorites were donated to the Natural History Museum, where you can see them. They are nicely exhibited. Even the piece of the roof of the cabin, which was hit by meteorite, is on the exhibit to see. But both were needed to be classified, yes, please. Because I especially use this word because the fact, even if this rock looks obviously meteoritic, it's not a meteorite until it's approved. So this rock has to be given a name, has to be described, has to be approved, and then it becomes meteorite. And a couple of facts is that the name for meteorite is always after the nearest town which has either a post office or train station. So like small collections of farms, even if they have a meteorite fall in the center, are unlucky that some other town will be given the name of a meteorite. Obviously, there must be, it's okay. There must be a convincing description of a fall or find, or how meteorites have been recovered, so that we are sure that it was a fall of meteorite and not something just from the cupboard appearing somewhere. And the description of the petrography, geochemistry, meaning like what is this rock, what it represents by itself. Just to say like what interesting can be in this rock. And in terms of the classification, I was the person who was doing classification of Oslo, so that's why I can show you a couple of stories from that. But classification of meteorite basically means saying what type of rock it is, and by that, what evolution it had, what was the history, and what kind of processes we can study with that. And very briefly speaking, meteorites can come from undifferentiated bodies, meaning that these are bodies where everything is mixed together and never went through any processes. So like very beginning of the solar system, everything got frozen and nothing happened to it. And these are undifferentiated meteorites, called also chondrites, after chondrule, these like the globular blebs, which were first solids or one of the first solids and are supposed to be building blocks of planets. So everything on planets was built out of these chondrules, which are preserved in chondrites. And the entirely separate group of meteorites are differentiated meteorites, which come from bodies like planets, like the Earth, more or less, obviously smaller. And generally speaking, they have core, mantle, and crust built of various elements which differentiated, that's this word. And among them, achondrites, called like just having no chondrules, but it's not genetic. These rocks look like our crustal basalts or rocks which we find on Earth, so they are quite tricky. And iron meteorites are composed of iron, so they are very heavy and shiny fragments of the core. So that's the first proxy of classification. And in case of Oslo, already on a first glance, it's very easy to say that it's a chondrite because we can see here these globules of chondrules. And here is a thin section, so like a glassy part of a meteorite, slice of meteorite glued on the glass to be transparent to the microscope. And on this thin section, we can see cross sections of the chondrules. So that's obvious that it's a chondrite. But obviously, science has to be a little bit more complex. So what kind of chondrite it is, right? And yes, please. Mm-hmm. To say that, we have to study a little bit composition of different minerals building this rock. And for that, we need an equipment called electron microprobe, which is available at the departments at the universities. And essentially what it gives is the elemental composition, chemical composition of specific minerals that form the meteorite. And by that, we can compare like composition of, for example, olivine and composition of iron nickel metal is characteristic for each group of this type of meteorites. And in case of Oslo, it turned out that it's an ordinary chondrite of H type. Oh, it worked now. And what does it actually mean? H is quite disappointing acronym because it just means high iron, meaning that this meteorite contains a lot of native iron nickel in form of these shiny grains. And ordinary means that it's one of the most common meteorites. And if you look at the statistics, out of 70,000 official meteorites registered and approved, almost 90% are ordinary chondrites. So this is actually the most common type of meteorite, and this is how the name is given. Okay. And just as a snapshot, in Norway, you have 15 meteorites. As you can see, most of them are ordinary chondrites, like these LH types. Not surprising. There is a couple of carbonaceous chondrites, so different type of chondrites. There is a pallasite, meaning stony iron meteorite, and there is one iron meteorite. I will not talk about them in details, but they are all, as I said, exhibited in the museum here, and you can go and see them if you are interested. And on top of that, data about all these meteorites are freely available through Meteoritical Bulletin. So if you are interested in that, just note this name and Google yourself. And now the question. We have 15, but will we have more? I guess everyone saw in the summer the fireball meteor over Oslo. And obvious question is like, where is the meteorite, right? And yes, we can expect fall anytime, anywhere, but as we all realized, we saw the fireball, none of us saw the meteorite, so actually how likely it is to recover them? Doesn't work? Yes. Yes, so meaning that there will be something, but the question, okay, can you, thank you. To help recovering, there is a smart initiative of surveying meteors. As I said in the beginning, meteor is this trail in the sky, which connects meteoroid from entry and meteorite on the landing. And if we are able to know which direction it actually traveled, maybe then we can pinpoint the location where the meteorite landed. And to do that, there are meteor camera networks which work in the way that at least 3 recordings from different sites, if we have them, then we can calculate the real orientation of the travel of meteoroid and calculate the fall of meteorite. And in this case, in Norway, there is an operating meteorite network, and it was lucky enough to have recordings of 5 cameras of this fireball which happened in the summer. And here are the example recordings. And from that, they calculated more or less the place of the fall. And it turned out that it's like 60 kilometers west of Oslo, in the area with probability like 3 kilometers by 1.5 kilometers, somewhere there is a meteorite. And now think that way, how easy it is to recover this from there. That's the photo of the terrain there, so it's like a total forest. And the mass of meteorite was estimated to be a couple of kilograms. So it's like, they're probably like a bag of apples somewhere in the forest, and actually we don't even know if it arrived as a one bag or it's split and there are apples everywhere, right? And now good luck and search for that. But obviously it's anyway interesting topic. So there was an organized recovery attempt led by the Red Cross who in very professional way approached that and set people in a line, like displaced by 1 meter, 1.5, as if we were looking for lost people. And we were like 4 days after the fall, 80 volunteers were surveying the area of this ellipse, this forest, to see if there is a meteorite anywhere. And it sounds quite cool, but the sad part is that after a whole day of work of these 80 people split into a couple of teams, we were able to survey only northern tip and southern tip of ellipse and nothing more. And the recovery attempt had to stop due to the personnel issues and so on. So large part of this is uncovered and probably will never be covered. And my conclusion about that is, like, more people we have during the search, more likely we are at least to be sure that we surveyed the area. Right, thank you. And it is important to survey them because meteorites disappear very quickly. Here is an example of a meteorite from Poland, a meteorite which I did my doctoral thesis on, actually. It fell in 1868, and there was like 200 kilograms of meteorites recovered immediately after the fall. And in the area of the ellipse, you can still find meteorites, but currently they look like that. They are totally rusted and not looking meteorite-like at all, meaning that all meteorites, including the one in Lear, after a couple of years will look more like that than like a meteorite, and recovery of them after each winter will be more and more difficult, right? Mm-hmm. Okay, so to very shortly say now why actually we are fascinated about meteorites and why do we study them if it's so difficult to recover them and so challenging. First is that they are samples from extraterrestrial bodies, but they sample various parts of the other bodies. On the Earth, if we have cross-section here, we have an access to the external crust of the Earth. The radius of the Earth is more than 6,000 kilometers, right? And the deepest drill, which we did, like to directly sample the rocks from beneath, was 12 kilometers. And in some places, we are lucky, due to some geological processes, to have rocks from the depth of 150, 300 kilometers put on the surface, accessible as small fragments. And if we try to imagine what is the distance, try to think that this 6,000 kilometers distance is more or less like a trip from Oslo to New York, more or less, right? And with drill, if we go for this trip, I don't know, it would be Sandvika or somewhere there, like not farther. So that's the distance of the trip if it was down to the Earth, which we sampled, right? While with meteorites, we have samples from all the layers, obviously not from the Earth, but from other bodies. We have samples from the crust, we have samples from the mantle, we have pallasites, which are samples from the probably core mantle boundary of any broken off body, and we have samples of the iron meteorites, which are probably like the terrestrial core. So that's that is one reason why meteorites are important. Mm-hmm. Another reason, even more important, is that they are very old and they record the birth of the solar system. If we imagine the time of the solar system, if we scale it to a calendar with the 1st January as a sun starting to, what's the word? Shine, right? To work. And 31st of December at the midnight as now, right? If we scale this time, it's actually quite surprising that the oldest oceanic crust is only formed on, preserved on 15th of December. Rocks which we are here in Oslo were formed on more or less 7th of December. And from the geological record, we have, like on the 20th of February, some very scarce remnants of oldest continents on Earth. And from this time, from January till mid-February, there's absolutely no geological record. While meteorites, formed on the very first day, and they stayed like that. And there is an archive of all these processes which happened in this time. And these photos show, for example, calcium aluminum rich inclusions, which were the agglomerates of the most refractory, the very first condensates in the protoplanetary disk which formed, or the chondrule, which I was briefly mentioning before, the first components of the planets. We still can access them in meteorites if we have them. And the third reason why meteorites are important is just statistical. We have 70,000 meteorites, as I mentioned somewhere briefly. And apart from that, we have a couple of samples which are delivered by quite costly space missions. But among these samples are only samples from the moon, totaling like 400 kilograms. We don't have anything from Mars, and campaign of getting samples from Mars is very challenging and very costly. And we have samples from 3 asteroids. Each mission brought something like 1 gram of material, and that's it. And apart from that, we have just free delivery samples of meteorites. So actually, they are our only material available really to study geology of the solar system. Okay, so that would be a summary to take-home message. Mainly, meteorites can fall anytime, and we might be lucky to see it. And I would say that if in these cases, it's obvious, no one has any doubt about if it is a meteorite or not. It's just everyone knows what they have. But anyway, it's good to contact an expert or someone who knows meteorites to discuss what to do further with that. The most tricky part is about these meteorites which are found by luck, because on one hand side, as I said, they rust very quickly and they do not look quite meteoritic. So it seems like each rock may be a meteorite, but believe me, not each weird rock is a meteorite. And can we?
Yeah.
Yes, thank you. And in this case, the best test is to see if there is a remnant of the fusion crust, but it might be not that obvious if it's very rusted. But the tip is, which was already in the quiz, that most likely it's an ordinary chondrite, right? Statistically looking, meaning that it will contain iron nickel, will be heavy and magnetic. And then it means that we probably can think about having meteorite. Can we come back? There's one back. Okay. And my message would be, if you are interested in meteorites, check the web pages of the Norwegian Meteor Camera Network. And if you are available, join searches to support the initiative of recovering meteorites, because they are really constantly falling, and there is a couple times per year a chance to have something which gets rusted because it's not recovered. And another thing is, never buy anything which is not approved meteorite. Never just get fascinated by it's a meteorite. Contact specialists, check in meteoritical bulletin. Meteorites are quite well registered, and it's not just a random rock. And the last part which I would like to draw to your attention is that it's quite rare that all national meteorites are curated and exhibited in one place. And Norway could be proud of that it's the case. And especially from the fact that they are all available to everyone in to view. I can tell you it's not the case in each country. In many countries, meteorites are spread among a variety of institutions, if kept in the country at all. Sometimes they are just in the drawers in the museums and never available for the public. So yeah, you should be proud of that, and you should take the opportunity to watch them. Thank you. And one more. Dziękuję za slajdy. To daję?
Yeah, thank you so much
Thank you.
Before we had a player during the quiz that was named Copernicus was a woman. I guess it was no, okay, never mind. Okay, okay. Because there was a Polish program that actually promoted women in science, and actually Agata proved that women also can study the space as well as Copernicus. So thank you for that. And now we can come to questions. You can write the questions. Actually, can you? Oh, okay.
Okay, you can write the questions on the app that Thibaut will display right now, but you can also ask directly. We have actually first question from online guest. So Gun asked, if I find a meteorite, can I sell it to the Natural History Museum, or must I give the stone to the museum?
That's a question which answer depends on the country. It's regulated by the governmental law. As far as I know, in Norway, the law is quite liberal in that. But anyway, I should say that I encourage to deliver these samples to the natural. The question was, is it sold or just donated for free? That I can't answer. I'm sorry, I don't know really. I guess it is with some benefits to the finder, maybe with some sale offer.
Okay. No, it's depending if they come to the search, then it's not as the same as if they find it by themselves.
Is it? Yeah, that's another thing. That obviously, if we join the search organized, for example, by Camera Network, then it's obvious that we volunteer and that the meteorite will be donated. But if someone is lucky to find a meteorite, it is a property of finder then, right? And should be sold.
Okay.
I guess.
Okay, you have the next question here.
How did we get them? Okay, so it's quite a complex question, but there are two things which are important to delivery of samples from asteroids. First is that asteroids are located in the zone which is very unstable dynamically, meaning that they start to orbit in a weird
Oh, no. We are. The first one was this one. Yeah.
This is about the space mission.
Ah.
about okay, samples from asteroids. In this sense, okay, we had 3 missions sent, one by JAXA, 2 by JAXA, by Japanese Space Agency, and 1 by NASA, American mission, which were sent to asteroids. And the sampling thing, if that's the question, the way of sampling was that the spacecraft was flying low above the asteroid, shooting a projectile to put a lot of dust and capturing this dust like a hoover.
It was not with people, right? It was
No. They are robotic missions.
Yeah. Okay, the next question, I guess.
It depends. Usually, we recommend to be as non-destructive as possible, but some analysis needs some grinding or cutting, and it depends, I would say, of the scientific value of the results, if we are allowed to grind meteorite or not.
Question: what if meteorite is to be radioactive? So we may be exposed to the gamma ray exposure in space.
They are radioactive. If you want to, we can talk about that. There is actually even a way of measuring meteorites, and if someone is cheating and saying that they just found a meteorite, it's possible to check if it was found now or comes from whatever collection, because the radioisotopes created in the space, some decay and are not active any longer. Yes.
Oh, we have the. Yeah.
Okay, I can speak.
But wait, for the online speaker. For the online speaker. Yeah.
Okay. Thank you for your presentation. This might be a stupid question. I don't know.
There are no stupid questions.
All meteorites found on Earth, are they from our solar system? I guess.
Yes.
Yes. Okay. Thank you.
Yes. As far as we know, yes, we haven't identified anything apart from asteroids, Moon, and Mars. We don't have any confirmed meteorite even from Venus, Mercury, while technically they could exist, maybe. So definitely we are sampling small and vast asteroids.
Yeah, I'm sorry. From bigger planets with bigger gravity, it's unlikely that there ever will be a asteroid.
Yes, there are some mechanisms which allow. It's called spallation. If you want to look more into these details, it is possible to eject some small portion of material from the bigger planets, but technically, even planets like Mars of this gravity technically should not eject material. Technically, it should be that the ejection velocity is that high that the material should get what's the word? Vaporized on ejection. So there is a small zone close to the surface called spallation zone, where the pressures are slightly reduced, and only by that the meteorites can be ejected. But for the large planets, that's the issue.
Thank you.
Thank you.
Any other questions? Oh, wait. I'm running. Yeah.
Will we search for more meteorites after the meteors we saw just recently?
The ones last weekend, I think there were two, right? One, as far as I know, landed somewhere in the sea, so probably not. And the other one was, I think, small. And yeah, we have to be aware that with the ellipse of being 3 kilometers, searching for something which is like an apple size, it's unfeasible, right? And probably not that even inviting for people, encouraging. So I guess answer is no. But we can come back to Lear if of interest.
Are the meteorites coming from universe origin or planet destruction?
Oh. Not universe origin. Well, I guess the question is what they need. Okay, they do need some destruction, right? To have, for example, iron meteorites from the core of the body, obviously this body has to be destructed, right? It has to experience catastrophic event that breaks it out totally. So in a way, they do come from the catastrophic disruptions, but not all of them. Some are just small aggregates from the very beginning, and they end up like that. So certainly they do not sample the universe origin, but yes, solar system origin, yes, and the catastrophic disruption as well, yes.
Yeah. In what country is there found most meteorites?
There is no rule for that. Actually, that's a thing which I promised to answer related to the quiz.
True. Yeah.
Yes. So meteorites fall evenly all around the world, including continents and oceans, right? So the first implication is that most meteorites are lost in the oceans. And each country gets the same amount of meteorites, but the problem is to see them, right? If we have a populated area, even like in Oslo, where people live, and meteorite fell, it was not that easy to see it, right? And probably there are still some pieces somewhere. in left, like not everything is collected. And so the thing is that more population density, more recovery likelihood, and more meteorites is there. And with the deserts, the thing is that, as I showed, in our climate, meteorites weather very quickly, and after 100 of years or 150 or something, they are useless. They disappear. While on deserts, there is no water, there is no weathering, meaning that they can stay quite intact for thousands of years, meaning that everything which falls is accumulated and accumulated. And this is why on deserts we have the largest amount of meteorites, but it's not that they preferentially fall there. They just accumulate there, right?
Okay. So I guess that's it. Thank you so much. And I guess before the next speaker, we will have 10 minutes break. Hello. Oh.
Hello.
Oh my gosh, I'm so sorry. Okay, I'm so sorry. I'm sorry. But I got the attention. So I'm glad that I think everybody is still here and to listen for our second speaker. Before I introduce him, I would like to ask who is outside of the field of space, astrophysics. Okay, so because we are constantly saying Copernicus, 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 does anybody know? I mean, does everybody know what Copernicus actually did? Yeah, that's true. That's true. That's true. What was his famous discovery? Huh? Yeah. Once again? The Earth goes around the sun. Yes, that is correct answer. So as you can see, similarly to Copernicus, who really discovered that, I think he calculated it.
Actually used it as a model. It was a very dangerous idea at the time, but he was a priest.
Yeah.
So he could use it as a kind of smuggle it as a model. He didn't say this is theory, this is a truth. He just said it's easier to calculate the movements of planets if we assume that sun is in the center. He was lucky because Galileo, who actually thought that maybe this is actually true, he was banished the church, and that was a big thing at the time.
Yeah, so actually you can give it back.
Yeah, sorry.
Yeah, so as you can see, our next expert is the expert on the sun as well as Copernicus. So Maciej Szydlarski, he is a again that's the difficult word. Computational.
Yeah, very good.
Perfect. Astrophysicist who got his education from universities in Poland, Italy, and France, to finally find home at the University of Oslo, at the Institute of Theoretical Astrophysics, which is the best place in the world, in his humble opinion, to be a solar physicist, of course. In front of the computer, you can find, if not in front of the computer, yes. You can find him in deep valleys and gorges of Norwegian mountains, where he pedals with his water kayak.
Yes. Water kayak. Yes.
Yeah. Yeah. Sorry.
Pretty much on.
Yeah. So, floor is yours.
Thank you. And I just don't want to brag, but actually, I share the same name as a Nicolaus Copernicus because Mikołaj, that's the Polish pronunciation for it. But I have nothing to do with it.
See, perfect.
But I'm more interested in the movement of the sun, not actually, I don't want to keep it still. And I wanted to open my talk with the underused statement that the sun is a star. That means if we look at during the bright night at the skies, and pretty much all the bright dots of the skies, those are the stars. Very like a sun. It goes, of course, in a different variety of sizes and the colors, much like the humans. The only problem is when the sun arrives from the horizon, it dominates our skies. It doesn't matter if you're on the Earth, like here on this photo on the left, or if you're on the Mars. There's actually two photos taken on the sunrise and the two different worlds. But what's so great about it? I mean, of course, it's bright and we're in that blanket of the warmth. But the great advantage of having our local star is that we can look at it in the great details from up close. And here it is. This is the sun in its true color. Actually, maybe this is a question to you guys. What do you think is the true color of the sun? Do you know?
Is it white?
Is it white? Exactly, it is. Sun is white, but it's actually need a little bit of extra explanation. First of all, what we call the visible light is only a tiny portion of something what we call the electromagnetic spectrum. It just happened that our brain, equipped with eye, just doing the evolution, tune ourselves to recognize a tiny portion of electromagnetic spectrum. The colors are also something what the brain interprets. We know that there's insects, which look at the ultraviolet, something we cannot see. We also know the reptiles, some of them can infer or look on the heat signatures. But sun emits light in the entire spectrum here. So what we can do, actually, we can put the special filter on the camera. It's not any longer the ordinary camera, but something special equipment. All right. Oh, geez, I feel like a karaoke scheme. I can put this extra filter on the camera, and then, I mean, you can select the wavelengths of this electromagnetic spectrum, and this is always tangled with the very hot plasma of the material, which actually sun is built of. And you see this, if we move forward or we shorten those wavelengths, the sun starts appearing with lots of structures. We suddenly see that the sun is more complex than just boring white ball. You see a lot of happenings, there's a lot of things going on. And as we climb up, we can actually look at the photons which have been emitted from very hot material. And you can see actually the temperature over there in the corner of my slides. And we're climbing up and you see more and more happening. And this way of looking at the sun, this is one way of sort of infer and look at the different layers of that amazingly interesting celestial objects. And maybe at this point, I mean, I will wait a little bit because it's such a nice video. And it's actually not the video, it's the measurements. It's taken by the satellites called SDO, Solar Dynamic Observatory. So it's a satellite hanging in the space when you can actually observe the sun at these different wavelengths. And the great advantage is that you can combine them. Why it's so important, and this is the only slide which consists a little bit of extra statistics. Yes, sun has a different layers. So the surface, I mean, from which all the sun is emitted is called the photosphere. Above of it is the chromosphere, and then is this super hot corona. There's a few stats. Yes, it's made of the hydrogen and helium. It's from 4.6 billion years ago. But all this you can find on Wikipedia. I'll just continue with my story. But then I have to mention that sun is also the huge magnet. It is built from the plasma, and plasma conducting electricity. So it's just a moving body, all continuously moving. And when it's steering, and you probably know from the elementary school, that if you have a moving electric field, that produces a magnetic field, or changing magnetic field, that produces the electric field. Of course, we cannot see or we cannot look at the magnetic field lines, because they're just the concept of, well, the physical concept. But here you can think about it that magnetic fields on the sun is a little bit like a motorway, which drives the super hot plasma. And that hot plasma we can look at, because when it's hot or it's just super hot, it starts emitting the photons in that UV, so ultraviolet wavelength spectrum, and then adding this extra filters, we can actually look at it. So this is what happened here. You can see the traces of magnetic field lines and that hot plasma following it. But that fields, it also tangle lots of energy. And unfortunately, in some rare occasion, that accumulated energy can snap. It means that the old material will follow this strong magnetic field lines, can just explode and may fly towards the Earth. And that's what we call the solar storm. And when these charged particles traverse towards the Earth, fortunately, we are well protected. The Earth, or Aga can actually prove that if I'm wrong, has this iron core, which by moving producing its own magnetic fields. So it means when those charged particles hits our own magnetic fields, it just can push towards the poles, and then those particles just collide with oxygen or nitrogen in our atmosphere, and they produce this beautiful phenomena like a northern and southern light. And this slide is about my job security, because the solar storms are so important because they may affect plenty of different instruments. We rely on satellites. Those satellites, of course, they are not protected by the atmosphere because they're flying just above it. So they are in direct contact with that cloud of charged particles could be emitted from the sun. But we have planes which are high up in the atmosphere, so not that protected. You have plenty of the sensitive instruments. And if that solar storm would hit the surface of the Earth, they could easily break that. So we need to understand how the active sun works and to protect ourselves and maybe work a bit better on the so-called the space weather. And maybe this is also the reason why we have so many instruments floating in space. And I already mentioned this Solar Dynamic Observatory, and this is something you can Google up. And all the movies I show you, this is easy to find out, and you can see those beautiful storms, which are maybe fatal for us if not the atmosphere of the sun, but it's so nice to look at them. But then we can also observe the sun from the ground, but we have to be careful with that. I already mentioned that the atmosphere absorbs majority of that dangerous for us light. I'm talking about ultraviolet, X-ray, to gamma. It means it absorbs and we never reach the surface of the Earth. But of course, we're using the UV filters, and that's something which eventually could reach it. The radio, which we use to communicate with the satellites, fortunately penetrates the atmosphere, so there's no risk here. But then if we would like to observe any object outside the atmosphere, we have to be careful with choosing the right place. And we have such place. I mean, it's belongs to Europe, even though it's very close to Africa. And I'm talking about Canary Island. So if you plan your vacation, choose wisely. You can go to La Palma, which is a prime spot for observation. And there it is. There's actually the Swedish Solar Telescope, for now the best European facility to observing the sun. But I have to tell you that observing sun is not a romantic job. What you really do, you sit in the basement, you're surrounded by the equipment which costs millions of euros, but you have really crappy chairs. And then during the day, when this is such a beautiful weather outside, you sit in that basement and you're just basically recording the sun in the great details. But what's so great about that part of the job is when it's finished, I can look at that, the night sky. And my colleagues, the night observers, they have to go in their basement and observe the stars where I can actually look myself at the starry sky. So why does the advantage of building the ground-based telescopes? Well, you can observe the sun, you can have this huge equipment which is otherwise so difficult to put in space. It's so costly and risky. Then you can just use a truck and drop it on the top of the volcano and just point at the sun and you can zoom into such great details. If you do so, you're probably gonna look like that. Because between you and the telescope, there's of course loss of air, or it could be turbulent, it can move around, and it's of course distort the entire object. This is one of the reasons why we also would like to go to the space, because space is a vacuum, there's nothing moving between us and sun, so we can observe it in great details, so on. But here, fortunately, it's the first part when the computer helps us a lot. Through some sophisticated algorithm, you can actually fix that, and you have a sharp object. And there it is. If you look at this boring star, this boring white ball, the great details, lots of things happening. Okay, for the effect, we can add the color, because color is a little bit fake in astrophysics. It's always just intensity. White means bright, dark black means a little bit less bright. So then, of course, in any program, you can add the color of any choice. You can also add the earth, just to give you the idea of the scale, what we're looking at. So all this kind of strange motion. How we explain that? And for that, we can use mathematical models or the simulations. And this is what our group is famous for. And this is actually the example from our simulation. As you can see, it resembles what we actually observe in the high resolution pretty well. So how do we get there? So we're using here a little bit what we call the star in the box. We cannot afford to have the entire star in our computer, but you can choose the small portion of it and just packed inside as much as physics and mathematical models that we can just to explain that phenomenon. So we model it and run it for time. Great advantage of that is it's not anymore the flat image. It's a three-dimensional object. So here is like a tomographic scan of that star in the box. So those blankets, gray color, it's this isosurface, something which will follow the constant temperature. And that's what we do, is come through that box and showing the different isosurface of the temperatures. Of course, if you look from above, you can see the dynamics of that model, how that temperature moves in space over the time. We can also add the additional information which you cannot add otherwise in observation. The blue-red color corresponds to the magnetic fields, which is this secret agent which drives that motions in the sun. How exactly that helps us explain what we saw before? So this is again that simulated picture, that intensity, but now I'm adding some slices from my simulation. And there, let's look first on the temperature. I think scientists like to put it in logarithmic scale. But take away from here is all those images somehow resemble that thing we observed before. This is a temperature. The red means a little bit hotter. The blue means a little bit colder. So since the patterns are very much alike, it means that the bright spots on that image, they're a little bit hotter, whereas the dark spots on that image is a bit cooler. Let's look at the velocity. The blue means there's something moving towards us, whereas the red means moving away from us. So it means that, again, the dark spots means that something is moving away. Of course, something is plasma. And the blue means it's moving towards us. That's a density. The bright colors means it's less dense, whereas the dark means it's more dense. If you combine those three elements, we solve the puzzle. Here, what's happening, this is an image of moving plasma, hot plasma moving from below the surface, the sun towards us, get cool down, move away, and just sink down. And this phenomena calls the convective flows. This is pretty much the same as you would boil the water, except of course this water is 5,000 kelvins, and it's conducting the electricity, and you would just die if you would just step on it. Again, another great advantage of that is with the model, you can flip it by 90 degrees, and rather than look from the top, which is our limitation when we're looking at the sun, we can use it from the sides. And again, we can see a lot of details. So on the previous slides, I just cut my simulation on that side, and now we're looking from the side, and you see here the evolution of temperature. So those are a little bit complementary. The red here means very hot. By very hot, looking at scale means the millions of kelvins, where the surface were meant to be about 5,000 kelvins. Here, the red means very dense, and the blue, a couple of orders of magnitude less dense. So it means that the corona, it's very like faint or light, but super hot, whereas this indicates a little bit of surface. But how we get there? Of course, there's a math. There's a lot of math. To be honest, I start with the partial differential equation. And this is something when you can see in every single Hollywood movie. When you want to impress, the viewer about some sophisticated math, you tend to put some signs like that. And this is just, it's not that complicated, really. It's just, this is a notation, with a lot of Greek alphabets. But this is just a set of rules. It's not something you simply solve on the piece of paper. It just tells you, how things change. In that case, the T corresponds to time. That means that it's a set of rules about the evolution of some quantities in time. Humans cannot do that, or to some degree they can if they simplify it. But you can just span it over the mesh. A mesh, think about it as an Excel sheet, when you can just fill it with the initial condition. Like every element will be filled with some temperature, density. And then you have those rules, which tells you how to move forward, how you simulate the evolution of the quantity. And that, if you just use that mesh and you sort of rewrite those sophisticated math, end up with something like that. And this is not complicated. It's a lot of division, multiplication, summation. So it's quite easy. It's just maybe so boring for humans to count it. So why not to code it? Well, in a little bit old language. But then if you pass it through a computer, you can send it to something what we call this. Oops, sorry for that. We can send it to a supercomputer. This is Pleiades. The supercomputers, they don't look so super. They're usually hidden in a big basement. It just happens that they are just the blocks of computers plugged with very expensive cables. And it happens that we are one of the biggest users of the biggest Norwegian computer called the Betsy. And they end up, people like, show the muscles, send the countries. They like to rank them and show who has the biggest machine. And the Norwegian machine is for now on the 62nd place, and it has 1,072 cores, whereas the laptops like this one maybe has 4 or 6 of them. This is nothing to compare with the top computers, like this one from Fugaku from Japan, where there's 7 million of them. And this is, of course, when we strive to use, and bigger machine means that we can actually tackle the bigger problem. But again, this is not such a romantic job as you think. At the end of the day, you just look at the plenty of screens like that. When you modify your code, you maybe see a bunch of numbers. I won't call many supercomputers, but you always just connect to them through the boring black and white terminal, and it doesn't matter if the computer is in Trondheim or it's in the Pasadena in California. At the end of the day, those codes also tend to be very complicated. The one I'm working with has 78,000 lines of code, which you somehow need to at least be familiar with. But it's also with that complexity, it means that it continuously breaks. And if any of you ever work with the code, it may relate to that plot, because this is how the work of the programmer looks like. You continuously fix some bugs, but when you fix one, then another appears. So this is sort of explain the everyday work of the programmer. So where are we going from there? So bigger machine. Remember that Fukatu, the biggest Japanese machine? That's my colleague who actually managed to fit his problem. He's not anymore limited to the box. He can actually fit the entire sun on his big computer and resolve it. And of course, this is something what we're also working on. And you're probably going to hear from us because we would like to tackle the same problem, but better. And I just leave you with this beautiful image of the active sun, which I gracefully omitted in my talk, because sun can offer so much more. And in order to see or explain this kind of phenomena, we need larger boxes and the bigger stars. So I gladly accept any questions, but this is where I am right now. Thank you.
Yes. Here you go.
Hello, thank you. Interesting. Maybe a bit on the side, but it's sun related. When a sun dies,
We're all gonna die.
no,
It's very grim
But
because
what-
today
what-
Agata Krzesinska was
but
about
they say
to...
like they do die,
Yes.
don't they? Say? Yeah. What physically or what happens?
So sun is gonna burn out its fuel. It's gonna be helium or hydrogen, and eventually it's gonna be out. So first of all, we have to understand why we know that, because sun lives for billions of years. Obviously, our lifetime is not that long, but there's something beautiful about the cosmos of space. You can just look around. It's the same like you spacemen would land on the Earth and look at the city. You have these children, you have adults, teenager, and it maybe require 10 minutes to figure out what's the life cycle of the humans. And we have the same by looking at the stars through the telescope. You see the stars at different stage of their life. We see the dying star, you see the newborn stars, and therefore this is the way how we can guess how our sun is going to end up. Fortunately, the star is not the rock star. It's not going to have like a super intense lifestyle. It means like slowly burning its fuel and make it to the elderly and just calmly fall down and become so something what we call the red dwarf. So it's get a little bit expanded and cooler, and the Earth will be swallowed if it's still going to be around it by some warmish plasma. So it's a nice way to go. Maybe not as spectacular like supernova.
Thank you. That was beautiful answer.
Well, we could add on the long before the sun goes, because it's increasing energy. Our planet is fucked in one another.
Yeah, that's right.
The ocean will be evaporized and gone.
So we're not going to
Sun
see
will still be
it.
there on the old days. Good luck.
Yes.
Okay.
For the future.
So it's very green topics we choose because we have a meteorite falling from skies. We have solar storms and dying stars. Very nice.
I have several questions actually. When you, yeah, I have at least three. I do simulation as well. So my question: can you simulate the entire sun?
Yes, we
And
can.
if okay, on what level? At the atom level, or you need to simplify?
No, of course, what we do, it's, I'm just omitted that part, but it's the partial differential equation. So the model I've shown, it's called the magnetohydrodynamics. This is like a fluid dynamics combined with the magnetism. But of course, there's approaches when we can distinguish the different atomic levels, and that's quite important, to be honest. For now, we assume that the plasma is just fully ionized. This is one model. But then you have a multi-fluid model when you recognize the neutrals, ions, electrons. So this is a little bit like atomic one. And then, of course, in your box, you have multiple fluids that interact with each other. And more powerful computer we get, the more of that physics we can inject in our, well, box first, but then we have that sphere. Actually, our approach is simple, which is stitch together plenty of boxes. And as long as we have enough memory or the computer is big enough, we can just go around it and build the star this way. But we're really interested in combining the small scale and large scale.
Yeah. Okay. And the last one is like, do you have like a concrete example of your research, or can you predict, for instance, next time I don't need to go? I mean, when do I need for sure to go to Soxvan to see the Northern Lights?
Right. So I have to admit that what we do is a little bit more fundamental. So there's a reason why I started with those beautiful images with the sun with the high resolution, because those two goes in pair, especially in our institute. Because those are two races. The one is to get to look at the sun with the highest possible resolution with the great fine details. And actually, I have a few examples of that further on, because this is when you start looking at the sun with the even finer the parts of the spectrum. We're talking about very low portion, and every single line here is a different wavelength. And if you scan through that tiny portion of wavelengths, you can see how much structure is evolved from that. Then another part, it's maybe looking at the combination of the two different wavelengths. And this is again the movement, and this is the lines which are sensitive to iron and actually show the magnetic field lines. So by looking at both of them, we can explain some of those phenomena. So I say that simulation is fundamental in the way that our model are used to generate those synthetic observable and compare it directly with observation. And then we can actually try to explain what's going on, what we see. So in that sense, I mean, we contribute to the fundamental understanding how the sun operates, but then another scientists which leech on that type of science or the results. And then, of course, they plug it to the predictive model. And this is what they do the space weather. But this is a little bit on the different level then. But yeah, that's what I would see. Yes? Two questions.
Yeah.
Maybe
Not necessarily the solar physics. I mean, I'm up for any question.
No, I can, but because this was directly
Okay,
on
so-
this one.
Okay, so it's directly on this one. So yeah,
Wait a minute.
So you just said that, but you have now all these numerical models, but how do you put it all together?
What do you mean by putting them together? I mean,
Yeah, well, you have showed us before all these different wavelengths and observations,
That's
and now you can reproduce that on the computer. So, what is the next to tell us about how the sun works?
right. So as you saw that the small one, we have the slices, right? I mean, what's different? I mean, what we get from sun, or to be honest, from any object in the far away in space, it's just light. Sure, we understand the atomic physics enough to know that lights can be emitted on different wavelengths, and that goes from the recombination of ionization of photons. So that goes back to the laboratory. But then, I mean, what's the actual physical process behind? That's a different story. So what I'm showing here is just, of course, temperature, density, the basic variables. But what we observe is just the intensity of very specific lights. So you're right, there's actually, on top of that model, you feed it to yet another process, which is super costly as well. And then you actually calculate, I mean, if you have this density in that point and that temperature, with that velocity, how much light is going to emit in that wavelength. And this is what we call the forward modeling. And that gives us the opportunity to compare it directly with the observation. And then if you see those images look alike, then you go back to that fundamental variables. And this would help us to resolve those riddles. Because then again, we have plenty of those high cadence observation, and you see something weird and bizarre happening. And then, of course, you have to run through model, and then you have a hypothesis. And models is always just great aid to understanding that physical process behind it. So this is how we work, and forward modeling is an important part of it.
I have one person here. I will come. Yeah.
Hi, yeah, I was going to ask, so what is the chance that during our lifetime there's going to be some kind of super ejection that wipes out all the satellite communication?
Right. Well, we live in a dangerous, first of all, there's the cycles. No, well, you've been close with that, because of course sun has the cycles. I've been prepared for this kind of question, as you can clearly see. And again, this is just observation, and the sun continuously follow that kind of cycles and become extremely active every 11 years, and then it calmed down and it became very quiet, and it became again very active. And of course, this is the season of storms. We have a few historical phenomena. We even find few on the traces of very old trees. I mean, and that's traced back to the 15th century. And we have something what we call the Eddington phenomenon in 19th century. At the time, there was a powerful phenomenon when you can see the northern lights in New York. Another time, lots of telegraphs being burned. Because what I mean, if the charged particles penetrate the atmosphere, they can induce the electric field. Of course, at that time, the most sophisticated device was the telegraph. But since then, we had only one phenomenon of the similar magnitude. But we are quite lucky. It was actually 2000, it was like 5 years ago, where it's a huge explosion, but it went in the opposite direction. So we've been lucky that we've never been hit. But we know that this may happen during our lifetime. So of course, I mean, if you actually go to the Norwegian pages about this disaster list, you will find that storm is among them. So there are the special means to maybe, first of all, predict it. And also, if you see that there's a severe storm coming, and as I think, again, I may be ready for that. Oh. So this is a little bit time scale. So first, what we see when we're observing the sun, see that explosion, as you prefer, and I don't like that word. You see that explosion in the sun, these photons traverse from the surface of the sun within 8 minutes. So we get that big light flash. So we know something is going on. But then you may actually get the X-rays. Those need more than 8 minutes to reach the surface, maybe 15 minutes. But no worries, they will be absorbed by the atmosphere. So nobody gets the fancy photographs of the skeletons. Then in the next few days, you get those energetic particles. This is what we should worry about. But those days about 4 days. And you actually get those recommendations often that you get the space weather forecast and tells like, oh, there was a storm on the sun. So please, all the pilots don't use the super high altitudes, avoid the North Pole because this is where you're exposed to this radiation. Of course, when that huge storm happens, again, we may have those 4 days to prepare ourselves. And maybe we get more recommendation to wear the foil hats and hide in the basement. Now, it's not going to be that severe. But for sure, I mean, those which is in the north of the both poles, I mean, need to be careful because maybe some of the transformators, I mean, for the electricity may burn down. And those devices have a break. And there's maybe 2 factories in the world who produce them. So, of course, the countries like Norway and Sweden, they store the extra one for that kind of occasion because we have an electricity outreach in Canada or Sweden because of the solar storms. So governments now know about it, and of course, they have the special means to at least be prepared for it. Not for super like a X-flare, like a huge one that we should worry about, but it's maybe once per hundreds of years, 1,000. So hopefully we're never gonna see it. Hopefully it'd be nice to see. Well, not in Oslo, it's on the challenge, but to see like beautiful northern lights in the close to equator, then you should worry.
Then actually I'm worried because like you can see the northern lights sometimes in Poland.
Yes.
In the northern part, like in Gdańsk, I think it was even this year. Should we be worried about that?
No, not at all. This
Okay.
is just a nice thing to observe. Sure, this is just the flares of they maybe reach the X-ray, but we are well protected then by the
But it was before like that also?
Yes.
Ah, okay.
People maybe
noticing
that and you know what it is. And you have to be lucky with the weather too.
That's true.
And know to face the north.
And
so
you
by
have
the way, the Norwegian weather forecast service, they recently added the KP index, which is basically just sort of cumulated index which monitor the solar activity or the solar wind activity. And you can associate it with any place in Norway. And if it's around 5 or 6, you have a high chance to see the northern lights in Oslo. So please check it out. I mean, it's ear.no, and you can just follow it. The best place, I think, for people in Oslo would be to go maybe Sognsvann. You have to face north and look low at the horizon. Of course, you can go Tromsø, but just check the ear. And now is the season of storms, so you may have a chance to look at the northern light.
Yeah, there you go.
Just a question about the models. So your colleague in Japan, I guess, has like the full sun model. So like what kind of
he's already done so much.
But what kind of variance do you see from like, your box model versus like scaled up? Is it worth the cost of like having like 7 million cores versus?
So we sort of, it's funny because you prove that the resolution is way to go. There's a lot of, we would like to resolve that large structure. So as you saw that box, what's the difficult part about it? There's a boundary condition. If you have this box, which is just not the whole, it's just part of the real reality, you have to define something on those missing parts, on the bottom and the top, because then, of course, you have to guess it. If you have the entire sun, then you don't have to do it. You can go with something much simpler. And then you just wait a little bit longer, you cook your atmosphere, and you get the same, maybe even better answer. So he done that and proving that, okay, this is way cool. If you resolution and size, we just keep on those boxes. You actually see the very nice physics which correspond to what we observe. So we know that's a good direction, but that unfortunately require like a machinery. So really good parallel code and big machine to run. So we're getting there. We are very close, actually.
I have a question for you.
No, I just want to add to one of the questions. Well, one thing is the change in the sun, but also very important is the change in the magnetic field on our own planet.
That's right.
Because that's protecting us. And, it's not that many thousands of years. The magnetic field almost was down to zero. And you also got UV radiation. That's also when people start running into caves and they actually use red mud and they put it in the face. It was the beginning of sun creams, and it's only, I think, 5,000 years ago. But that's our own shield is also a factor.
Right.
Yeah.
But it's more the question to geologists. I mean, how well they protect there.
Yeah,
there you go.
I'm a geomagnetic.
Yeah, there's another question.
No, my field is Earth magnetism. So.
There you go. But is the Earth magnet going to flip? Because it's continuously changing too, right?
It's on the way down, but you never know because it's on the way down, and historically then it can go up again. So you never know.
That's right.
I once was interviewed in the TV program on this, and I was going down. But when I said, if it's following that, it will go down to zero in 500 years, and they never showed it on TV because 500 years was too long.
That's right.
It was boring. They want to know what's happening tomorrow or next week. So and that was filtered. No interest.
That's right.
Amazing.
I'm sorry, there was a question from the back of the.
Oh yeah. Ready.
Thank you. So there was the solar probe that was launched fairly recently. So
solar probe.
Yeah, you were. Sorry.
I'm sorry.
So did you say that you were part of that? Or no?
Oh, of course, as a team, we were part of it. All major missions. I mean, that's why I say that Oslo it is one of the best places to study solar physics, and it's not exaggeration here. I mean, we've been involved in all major missions. Doesn't matter if they're made by JAXA, Japanese Space Agency, or NASA. So those models I've shown you that just often the key component of in preparation phase, especially. Maybe important. The Parker probe, not so much, but I mean, not the direct, but for everything else, when it involves a bit more like this is in situ observation, means that they just probe the plasma. There is not so much of the taking the actual images, but everything what takes images, then we're often very much involved.
Yeah, so the kind of the data that they're going to get, is that kind of stuff that you feed back into your models as well? Or?
Yes, for instance, what we're doing is a little bit idealized model. It means that the plasma is just, we assume there's one fluid, which is not really a true. The reality is there's just a soup of many ions, not only hydrogen and helium, but actually also the heavier elements. And this is exactly what the probe, the Parker probe, is trying to measure. It just opens a tiny window and just gathers this solar wind inside and counts the different ions. So it can tell us about the proportion of different ions in that solar wind, which help us tremendously because I can go back to my box and retune it and maybe have a completely or better understanding of all these dynamics, because maybe those effects of partial ionization is really important for us. And this is how to have those starting condition, we have to measure them.
Cool. And I had like a follow-up question that was like, when you showed us kind of like the original, like the first model, and then you kind of like showed like an actual, and this is an observation of the sun, and you're like, we can see that they're like pretty close. Like, right. Is there some kind of like measure that do you do some kind of like statistical thing to see this is a good model, this is a bad model? Just kind of like look at it and be like, yeah, this looks like what we're seeing.
It's actually quite strict confirmation. And this is something which I already tried to answer, but maybe more technical terms. It means that this model solved the distribution of these basic physical quantities, right? Like a density, temperature, velocities in the 3D space. This is the input model. From there, we calculate, okay, if I know the distribution of those elements in space, how can I calculate that block of the mass, that temperature with that speed, emit the light with that wavelength, this much, I mean, with the UV, this much X-ray. And this is what we call the forward modeling. And these images we get. And those we can compare one-to-one with the observation. And this entire machinery is so sensitive. So if you do something wrong with the modeling, you're totally off with the image. So even if the part looks alike, I mean, those intensities could be totally broken. So that means it's very rigorously tested. We never tried to simulate the actual like a movement. It just came out by itself. So it means you start with something still, you just turn the physics on, you wait long enough, and you see those granulation, what we call, that means this convection start working on, and the scales is exactly the same as we observe on the sun, which give us, of course, the confidence that we're doing things right.
Cool. Thank you.
Anybody else from the audience? Because I know we have I know that we have the online question. Yep. What is the temperature of a near vacuum?
A near vacuum.
Near vacuum.
So we have a CMB, cosmic microwave background. It means that we have this first light which fills the entire universe, and this is around 3.6 kelvins. So it's not zero, there's always a little bit of tiny warmth in the space. And this is something which allows us to look at the first light that ever emitted in our early universe. So maybe my answer would be 3.6 Kelvin.
Okay.
Or let's make it 0.7.
Yeah. And what is the age of the sun related in a way to human age? Is it a strong 50 years old, or young old in the 70s, or an old person in 90s?
We're approaching 50s. I mean, it's 40ish. It's already calm, well-established star. It's done his crazy time, and it's just now on his way to sort of enjoy the life and slowly burning all the remaining fuel. So it's all good. So plenty of time.
Okay. No middle age crisis?
No, I hope not. Or maybe all the storms we're talking about, this could be a little bit of middle age crisis. Hope not.
Okay, anybody else? Okay, then that's it, I guess. Thank you so much.
Just wrong direction.
That's it? Should I finish?
Yes.
Yeah, achieve it.
Yeah. Okay. No, okay. No, okay. Okay, that is from our side. Unfortunately, our third speaker could not be with us today. But thank you so much. Thank you so much for coming. And I hope to, I hope to see you all next time. Stay tuned for our next event. Thank you. Next event.
No, please fill out the feedback. We need it.
Feedback.
Don't you understand my French?
No. Malheureusement.